This video is about miniature circuit breakers, which are one of the most fascinating and essential component in our electrical systems. These tiny but powerful devices play a crucial role in keeping our homes and workplaces safe from electrical hazards. Although it may seem puzzling at first, the inner working of an MCB is built upon fundamental principle of electricity. Before we dive into the details, let's get a clear understanding of what an MCB is and why even we use this device. In an electrical system, two major types of faults are there: overloading and short circuit. A short circuit occurs when a direct connection between phase and neutral form due to some unpredictable reason. On the other hand, overloading occurs when the load on the system increases above its recommended value. In both situations, the value of current exceeds its recommended limit. This excessive amount of current creates lots of heat, which can burn the wire and can cause some serious problems. Here comes the role of miniature circuit breaker. Normally, a miniature circuit breaker is connected to the phase wire. However, in certain situations, a two-pole MCB is used instead of single-pole MCB. This is done because a two-pole MCB offers an extra level of protection by also including the neutral wire. MCB is a self-operated switch. It means when current rises above its recommended value, a MCB automatically trip and protect the system. In earlier days, a much simpler device known as electric fuse was used to protect electrical systems from the overloading and short circuit. A fuse is made of a wire that uses a metal alloy with a low melting point. When the current in the system exceeds the recommended value, it generates excessive heat in the fuse wire. When it gets too hot, the fuse wire melts because it has a low melting point. This action breaks the electric circuit, which helps to protect other electrical equipment from damage. The main downside of using a fuse is that, whenever the fuse wire melts, we have to manually replace it with a new one. But in case of MCB, no such problem is faced. When a MCB trips due to a fault, we can easily switch it back on after fixing the problem. Unlike a fuse, we don't need to replace anything. Let's explore how a miniature circuit breaker detects short circuit and overloads by understanding its internal working. The internal structure of a MCB can be divided into four main sections. First section consists of bimetallic strips. Second section is the arc chamber. Third section contains electromagnetic coil and operating mechanism. And the fourth one houses the connectors. As we discussed earlier, an MCB is always connected in series with the phase wire. In an MCB, load current flows through bimetallic strips and electromagnetic coil. A moving part known as a plunger is responsible for making and breaking the connections between the input and output connectors. When current passes through this coil, a magnetic field forms around the coil. As the current passing through coil is an alternating current, the magnetic field form is also pulsating in nature. A cylinder made up of a ferromagnetic material is placed inside this coil. The magnetic field of the coil exerts a force on the cylinder due to a phenomenon known as electromagnetism. At normal current values, a spring won't allow the cylinder to move because the force developed in the cylinder cannot overcome the spring tension. But in case of a short circuit, the value of current can rise to 50 or even 100 times of its normal value. As a result, a much stronger magnetic field is created, which applies a significant amount of force on the cylinder. Due to this force, cylinder move and trigger the operating mechanism, causing it to immediately cut off the circuit. But it is not over yet. This sudden interruption of current can cause an electric arc to form between the contacts. The temperature of the electric arc can go as high as thousands of degrees Celsius, which can easily cause damage to our MCB. To solve this issue, we use a component called as an arc chamber. An arc chamber is designed to split this arc into smaller pieces so that the energy of arc can safely dissipate it. And that's how a MCB protects the electrical system from short circuit. But what about an overloading condition? An overloading condition happens when you use too many appliances simultaneously. This condition puts too much load on the system. As a result, the current passing through the circuit breaker goes beyond its safe limit. In an overloading condition, the current is higher than its usual amount, but not as extreme as in the short circuit condition. Because of this, MCB is not tripped by electromagnetic coil, as we saw in the short circuit condition. Instead of this, in overloading condition, MCB uses bimetallic strips to trip the circuit. A bimetallic strip is a component made up of two different metal bonded together. These metals have different coefficients of thermal expansion. It means that, when these metals are heated, they expand at different rates. When an overload current passes through bimetallic strips for a few seconds, it generates excessive heat in the bimetallic strip. Due to this excessive heat, a bimetallic strip bends and triggers the operating mechanism. Please note that a short circuit is much more dangerous than the overloading. That's the reason a circuit breaker quickly trips within 2 to 5 milliseconds during a short circuit. But in case of overloading, it takes few seconds to trip. Please like this video and don't forget to subscribe my channel.